All right, page 431. This is 14, hiker out on Long's Peak. So they're hiking along. They look up at the peak. This would be my peak up here at some point, and they see an angle of elevation from where they're at of 30 degrees. And then they move 1,000 feet closer. So I'm assuming that that's 1,000 feet flat. And then they take another measurement and it's 35. So that makes sense. Like if I'm here and I measure an angle to the top corner of that room, as I move closer, that angle is going to get bigger, right? So the angle got a little bit bigger. That is actually enough information to figure out how tall the peak is, which is what they're asking. But it's not straightforward how this works. So I'll kind of walk you through my thought process. And when I was working with the student yesterday, I had no idea how to do this problem. I was in the same boat as you guys. So I'm looking at it and I'm like, there's a nice right triangle right here. Actually, I see two right triangles, right? You see the big one and then the small one, they overlap each other. They both share this side here, X. And I'm looking at it and I was like, man, if I knew this value right here, I'd be on easy street. I could write a tangent equation and I could solve it, right? But I don't know this value. So what do we do when we have something that we wish we knew, but we don't know what it is? We give it a name, right? So what do you want to call it? Give me a letter that's not X. Y. Okay. We'll call this Y. If I knew what that was, then I'd be able to figure out X. Actually, I could, with either of those, I got two different triangles. Ignore this line right here. If I knew what this was, I could add it onto 1,000 and then I'd know the base of this big triangle too. So I don't know what it is, but I think it's probably important, so I gave it a name. And then I'm kind of poking around, is there anything else I can do here? And I just wasn't seeing anything. So I decided to start writing some equations, and those equations are going to have some X's and Y's in them. Does anybody have any other ideas before I kind of go down this path? What were you thinking? Sure. Up here? For this big angle up here, this would be 60, yeah, absolutely. Because 90 and 30, we would need another 60. And this smaller top angle, we could find that also, that would be 55. So we do have those. Yeah, let's go ahead and put them in. This angle would be 60. And this angle would be 55, right? Because the angles in a triangle add up to 180. Okay. I think we're still kind of in the same problem though. The only way I can think of to find this side right now is if I had this one. Other ideas?
Plugged in. And okay, we solved for like.
You want to show me on your paper?
Yeah.
Let me see what you. Where am I looking here?
Okay, so I started over here and then I can figure it out.
Yeah. That's where we're headed. Yeah. Yep. So yeah, good for you. So same idea. I don't really know where to go, so I'm gonna just start writing some equations. What kind of equations could I write? I'm looking at this small triangle here, and I got opposite and adjacent. It's a right triangle. I could do a tangent equation, right? I don't know how it's going to help me because it's going to have an X and a Y in it, but let's go ahead and write it down and maybe we'll find a way to use it later on. I'm going to go tan 35 equals tangent is opposite over adjacent, so it'd be X over Y. That's basic right triangle trig. My geometry students could do that. Are you guys good on that? Now, we can't solve it, obviously, because it's got two variables in it, but okay, we got an equation at least. Let's see if we can write some more equations, and maybe then we'll see a way that we might be able to put some of those equations together. So then I'm looking at the big triangle is also a right triangle. This one with the angle of 30 on it. It would have X in it, right? But the base, I don't know what it is, but I know it's 1,000 plus Y, right? So let's write an equation with that. Tangent, I'm using the 30-degree triangle. It still has, the opposite is still X. But the adjacent, the bottom of this triangle is 1,000 plus Y. you had a couple different variables, but you were kind of, that was kind of the starting part for you as well. So I wrote this out. I'm like, okay. Maybe there's some way I can put those two equations together. And the next thing that caught my eye was that they both had x's in it, and the x's were kind of isolated. So my next idea was maybe I will get these x's by themselves. That would be pretty easy to do. I could clear these fractions. So let's clear the fractions, and then both equations are going to end up equaling x, and then maybe we could stick them together. So that's what I did next. So if I cleared fractions, I'd multiply on both sides by y here. We get y tan 35 equal to x. And if I clear fractions here, I'd multiply both sides by 1,000 plus y. So 1,000 plus y tan 30 equals also x would be all left over if I cleared that fraction. Look that over, make sure you're feeling confident. I didn't show my work there, but are you okay with what I did there? Now both equations are equal to x, so I can put these two pieces together, and then I should have an equation I can solve for y. And then once I have y, then I can go back and figure out what x is. All right, so since these are both equal to x, I can put them together. So my new equation that's only going to have y's in it would be tan 35 equals, instead of writing x, I'm going to write something else that x is equal to 1,000 plus y times tan 30. And we can definitely solve that. It's going to be messy, but it only has one variable in it. Any questions up to here? From here, we're just using algebra skills. This is not algebra 1 level. This is algebra 2, but you see y's on both sides. We know we're going to have to get all the y's on one side. That's how we solve. And then we'll probably have to factor out a y and do some division. So I think I would probably deal with these parentheses here, or multiply everything in the parenthesis by tangent 30. So we're just distributing. That's what I did in my next step. All right, now I'm free to start getting terms where I want them in my equations. So I don't want y's on both sides. So I'm going to get this guy off of here. So the y tan 35 is going to stay. And if I subtract this from both sides, we'll have minus y tan 30. And then we got 1,000 tan 30 over here. We saw this come up a whole bunch last semester. How am I going to get y by itself here? Now that I got all my y terms on one side, what's my next step? Factor it out. Factor the y's out, and then you'll just be able to divide to get y by itself. There's y's in both of these things, right? Factor that y out. This was something that a lot of us struggled with when we were doing inverses. Okay, this is a pretty common, this is going to come up a lot next year for you guys, where you have two messy looking terms on one side of an equation. You're trying to solve for something that's a factor of those terms. You got to factor that thing out and then divide. That needs to start becoming second nature too, okay? So now I got this y here, it's being multiplied by something, so I'll just divide both sides by this big old mess here. And there's y. Hooray. It's not even what I was trying to solve for, but at least I know what it is, right? Isn't that fun? Now check this out. X is just y times tangent 35. So I just need to take this and multiply it by tan 35 and we'll get our final answer. Cool. Any questions about that? Will not be on your test if anybody's thinking that question. Okay. Do you know why I wanted you to do this problem? You're going to see another one in your review like this. Do you know why I want you to do these problems? Because I want you to appreciate next semester or next unit when I teach you about the law of sines that you don't have to do this anymore. There's a much easier way to do this. We just haven't learned it yet. Or at least not in this class. Have you all learned about law of sines and law of cosines? Did you do that last year? I think I was told that most of the Algebra 2 teachers didn't get to it last year. We'll learn it in chapter 5. It'll be awesome. You'll be able to do this whole thing in like 2 steps. For now, we're kind of stuck with SOHCAHTOA. All right, 17. Yes, somebody asked about 17, so we'll do it. I didn't get a chance to finish sketching it here, but this was about a Coast Guard cutter. And when they give courses, by the way, anybody here into fishing, sailing, anything like that? When they say that you're on a course of 95 degrees, that means if you were to point yourself towards due north and turn clockwise, so you hit 95 degrees, that would be where the direction you're heading. So here's due north. If they say they're on a course of 95, I need to turn clockwise until I hit 95 degrees. That's the direction they're heading. So that's what a 95-degree course means. So 95-degree course, and they kind of give you a picture to help you see that. They're going 30 knots for 2 hours. How many nautical miles are they going to travel in 2 hours if they're going 30 nautical miles every hour? 60, right? 2 miles an hour. I'm sorry, 30 miles an hour for 2 hours will get you 60 miles, right? That's, yeah. Don't knots are just it's like miles per hour, but it's not miles per hour. It's nautical miles per hour, which are very close to the regular miles per hour. I don't know. So they're going 60 miles. So I know that that distance is 60 at 95 degrees. And then they turn to a course of 185. Again, remember that's always from due north. So if I go 185, I'd be going in this direction now. And this time we're going to go for another 2 hours. Okay. They didn't say anything about changing speeds. So I'm going to guess that's also 60. Says determine the distance and the bearing from Fort Lauderdale to the boat. Did they start at Fort Lauderdale? They did. So the Fort Lauderdale's here. So they want to know how far this is going to be. Oh, cool. And they also want to know what direction it is from due north. All right. So far, so good. How many of y'all figured out this is a 90-degree angle right here? This is 5 degrees bigger than a 90-degree angle, right? And this is 5 degrees bigger than a 180-degree angle. So from 95 to 185, that's a 90-degree angle. Agreed. This is our right triangle. Not only that, it's an isosceles right triangle, isn't it? So what would this angle be right here? This would be a 45-degree angle. Now that's not our bearing. Our bearing is going to be from due north all the way around to that. Let's talk about the bearing first. So I'm here and a 45-degree angle. Now it's 45 degrees off of, how do I want to do this? Oh, this is starting to confuse me now. This is 185, right? And then what would, that gets us to this direction. What's this right here? This is meant to be a straight line here. 180 minus 45, which is 135. Do you see why that's 135? So from north, we would go around 185 plus another 135. What is that? 185 and 135 is, you guys are looking at me like I'm going to give you the answer. I don't know the answer to that. What is it? 310? 310? 320? 320. Okay, so the bearing here would be 320 degrees. Ask me a question if you're not understanding why that is. The bearing is the angle from due north. So if I were standing at this spot right here, okay, at this spot right here, and I looked due north and I rotated all the way around to that direction that you'd have to go to get back to Fort Lauderdale, that angle right there would be my bearing, okay? So my logic is that we already did this up here to get to this line, right? We rotated 185 to get around to there, right? And this is 45 degrees off of there. So we've already rotated around 185. We're going to have to rotate around now another 135 to get back to this line. All right. And then how are we going to find this distance here? Yeah, we could use special right triangles. We could do Pythagorean theorem, right? We could do SOHCAHTOA. We got a 45-degree angle and a right triangle. So I'll leave that last part up to you. What other questions do you guys have from this assignment? Sure. That was from 4.7, right? The inverse stuff. 13 and 16, love to. Which one? Who's got a preference? That'd be a good idea. 14 or 16 then. 14? Awesome. 14. The book says arc sine. Arc sine of 0.67, which is just the inverse sine of 0.67. Use a calculator to find the approximate value, express your answer in degree. I think they're really just saying plug it into your calculator. Second sine. Now, they said they want the answer in degrees. We could go ahead and put our calculator in degree mode, and it will just give us the answer in degrees. So yeah, a lot of people had questions about these because they're like, is it really just type it in your calculator and write down the answer? It's like, it seems too easy, but it absolutely is. It's like 42.1 degrees. Well, so you got radians, but if you use your conversion skills to convert radians into degrees, that would have gotten you there. No, it's fine. It kind of threw me for a loop too when I was first looking. I was like, really? Is that all they want us to do? Oh. No. I'll show you something in a minute here though. You guys will love, appreciate. Any other questions? 29? 29. Ooh, these are fun. Are you okay with me changing that arc sine into an inverse sine? Okay, it says arc sine in the book, but it means the same as inverse sine. And I just prefer to see it that way. Now, those of you who are doing our little memorization quizzes are going to know what the cosine of pi over 3 is in about 4 weeks. No, 6 weeks. What is the cosine of pi over 3? It's a half. But let's say you don't know that. Let's say you haven't memorized that. So we're going to need to find that first. We work from the inside out. So cosine of pi over 3. So the first step in doing that is to know where pi over 3 is going to be on our unit circles. So we got to find that direction. Pi over 3, well, here's pi. So a third of pi would be like here-ish, right? And most of us are probably still mostly thinking in degrees. How many degrees is pi over 3? 60. Oh, look. That reference triangle is going to be a 30, 60, 90 triangle, which is 1, 1 radical 3. Or sorry, 1, 2 radical 3. The 2 is the hypotenuse. The 1's across from the smaller angle. The radical 3 is across from the bigger angle. And we're looking for cosine. which is adjacent over hypotenuse. Lo and behold, it is a half. So we found that that's a half. We're now looking for the inverse sine of 1/2 because this is 1/2. We'll be okay so far. And this one was pretty straightforward. Remember though, if this ends up in another quadrant, you will have to be thinking about whether it's positive or negative. I didn't ask that question because it's in the first quadrant and everything's positive in the first quadrant, but don't forget to do that. Good. All right, so I'm going to do inverse sine of 1/2. So I'm going to make myself another reference triangle. I know my answer is going to be an angle, by the way, because it always is when we're talking inverse sine. I need to remind myself what two quadrants I'm allowed to get out of an inverse sine. So it's negative pi over 2 to positive pi over 2. It's going to have to be one of these two. And the way I know which of those two it is based on the sign, S-I-G-N, of the 1/2 here. This is my ratio. If it's positive, that tells me which quadrant it's in because sine is only positive in one of these two quadrants. It's positive here. So my reference triangle for inverse sine of 1/2 is also going to be in this quadrant. So I'll go ahead and draw myself just sort of a generic looking reference triangle. This is my angle here, and that angle is going to end up being my answer. I got to go 1/2. So sine is opposite over hypotenuse. So 1 here, 2 here. That's another 30, 60, 90, isn't it? And 2 root 3. Would this be the 30 or the 60? It's across from the smaller side, so it must be the smaller angle. So it's going to be 30. So it's 30 degrees, but typically we want our answer in radians. 30 degrees is the same as pi over 6 radians. All good. Thanks for asking about that. Any others? Anything else? Alrighty. Let's talk what's going on going further.